All right, so before we do get started, I just want to mention, well, I guess one thing about the projects that are due today. I know some groups have invited me to be a collaborator on their repos. If you have not yet, please do that on GitHub. So go on your settings on your repo and invite me to be a collaborator because I need to have access to your commit history to make sure that you all work together. All right, that was a quick parenthesis there. Now talking about today's class. Before we do get started, I do want to say that tidymodels is a family of packages in itself, and we're going to talk more about that. But the reason why I asked you to install that before you came to class is because it may take a little moment to go through, and also because it may give you some trouble. So a couple of things that when I was updating on my side and I noticed it happened was it may ask if you want to, well, I guess the first thing is if you're installing on an RStudio environment that has already loaded some packages that tidymodels also load, it may ask you if you want to restart R or not. You can say no, and it's going to go through. Once it starts going through, it will say something like, there are some packages to upload. You want it to be updated from source, yes or no. You can say yes in the console, and then it's going to go through. And the last thing that I noticed on my side was when I tried, so it went through, and it takes a moment to go through because there's a lot of stuff being installed. But once it goes through and you try to use a library tidymodels, it may give you an error for rlang, saying the rlang version is one version, and then it's trying to use the newer one. If that is the case, you can do an install.packages on the rlang package if you get that error. So that should install the newest version of rlang, and then you can restart your R session. So it kind of like unloads all the packages and you restart fresh, and that should fix it. So I guess let me ask, was anyone able to go through this and install tidymodels successfully? Okay, I see some heads shaking. If you were not, what I wanted to propose is that given what I just said, which at least were the issues that I ran into, try to go through them as I am starting with the lecture, because we're going to have to be talking about some theory before we get into the coding that will require tidymodels. So if you can try to move through that as we are introducing the theory, I hope that by the time we get to the coding part, you would be able to actually code along. If you're not at that point, let me know, and we can try to troubleshoot for a moment before getting started with the coding part. All right, so I did send you an email earlier this morning asking you to create the whole workflow for a new project. The new project name was 11_elasticnet. So as you remember, and I hope you have already done this, you would start off on GitHub, create that repo on GitHub, copy that, come into your computer, create a new RStudio project using Git, the Git option, and then do it this way, because then it already connects your local Git with GitHub. And then you would create the subfolders code, data, and output. You would move into the code folder, the script I sent you, which is 084 or 0418 elasticnet partial. And also we're going to be using a data set that we have already wrangled. So this data set I did not share with you. You already had it on a different project. So you had this on the data folder of the 09 open data project. So I asked you to copy from that project and paste here. If you were able to do all this, then we're ready to get started. Go ahead and launch that RStudio project, and we'll start with the exercise. Okay, so I guess last exercise that we had, we did PCA and k-means. If you remember, PCA was one of the potential solutions when you have multicollinear data, right? And we could, if we wanted, first run our data through PCA and then use the PC scores to do any machine learning model training that follows that. I want to show you a little bit of a different approach. So if you remember, we talked about there are a few different ways to avoid multicollinearity. One of them was to select variables by hand, pretty much, which is just you looking at highly correlated predictors, removing the ones that are highly correlated, and then just keeping a subset by hand, pretty much. Another way was to use an algorithm that does that for you in some way. So that's what we're going to be talking about today. We're going to be, at the end of this exercise, we're going to train an elastic net model. If you've never heard of it, don't worry, we're going to go through that and you will understand what this is, but that's what we're going to accomplish by the end of today. So our learning objectives for today are going to be to understand linear regression penalization types, and then use a machine learning framework to pre-process data, train an elastic net model, and evaluate model predictability. If you remember, these three larger general classes of the workflow are things that we talked about in the lecture. This workflow will apply pretty much to any machine learning model you train. So what I want to introduce to you today is a workflow that you may change the algorithm, you may change the data, you may change different things on it, but overall, the workflow is going to be very similar, regardless of what machine learning model you're training. So let's start talking about the algorithm that we're going to be running today and trying to understand what it's doing for us. So we already discussed that on linear regression models, if you have variables, predictor variables that are highly correlated, you will suffer from multicollinearity, which is an issue because your model coefficient estimates may be biased, they may be in the wrong direction even, and your standard errors are going to be inflated. On the previous exercise, we talked about a few different ways of overcoming that. So one would be, again, dimensionality reduction. In the case of PCA, it doesn't only reduce the number of dimensions, but also creates dimensions that are orthogonal or independent or non-multicollinear. If you remember, the PCs are going to be independent and will not suffer from multicollinearity. We can also do variable selection, right? So instead of using all of our variables and transforming them into a non-correlated form like PCA does, we can select variables instead. One of them was by hand, we just talked about it, which would be if you basically look at the pairwise correlation between all of your predictors, like we had the matrix in the previous exercise, and you look at the pairs that have a high correlation and you keep only one of the pair, so you don't keep both. And then you use that model. But we can also do variable selection by models. And that's one of the things that I want to show you today with penalized linear regression models. So even within the models category, there are going to be different models that do variable selection in different ways. The one that we're going to be exploring today is going to be, we're going to apply a regularization to the linear model in the form of a penalty. And we're going to talk about two different types of penalties here. So if we just think of linear regression as, so not penalized linear regression, but just linear regression that we're fitting with ordinary least squares, which is what we've been doing up until now, which is prone to multicollinearity. The goal of the linear regression, of any linear regression, is to minimize the sum of squares of the error. So what does that mean? Here's just an example. It's not from our data, but we have a given X variable, a given Y variable, and we have a scatter plot. I mean, I'm sure that at this point you can look at this, you can say, yes, this is a regression. I see a line going through the points. This line so what is determining where this line is in this plot is the intercept and the slope. When the model is being fit behind the scenes, the intercept value and the slope value are the only two combinations for this data that minimizes the distance of the line to all the points. And that distance from the line to all the points, which here is that gray bar connecting the point to the blue line, is the residual. So the model is being fit, the coefficients are being found and calculated in a way that they minimize the distance of all residuals to the line, not just one point, all of them, right? With that, this blue line here, if it were just a little bit tilted up or downwards, the standard error, the sum of the squares of the error, which is the sum of the squares of the residual, would not be the minimum value, right? So imagine this blue line here being just a little bit tilted lower or higher. Any other position except from the one we're seeing will not minimize the SSE. There's only one solution, which is what we're seeing here, which is what gives us the slope and intercept for this data that minimizes the SSE, which we're seeing here on this model fit. So the function that's being minimized in any linear regression is or the function that's being optimized is trying to minimize the sum of the squares of the error. So minimize, again, the distance of all points to the predicted line. And there's only one solution that gives that minimization. Now, so that is just regular linear regression. That's what happens when you run any linear model, any regression model. Now, with regularized linear regression, there are going to be different types of penalties that would be applied to this function here that is minimizing the sum of the squares of the error. The way that this happens is the different penalties that are going to be applied, they will impact the coefficient of each one of the predictor variables. So imagine in our, I'm not presenting that model here, but imagine in your head, if we had strength being explained by each of the 74 or 72 weather variables, right? Each one of those variables are going to have a coefficient. And those coefficients some of them will suffer from multicollinearity because they are multicollinear, as we already established before. When we use some type of penalization on minimizing the standard error, what that penalty is going to do for us is basically two things, depending on the penalty. One of them is going to look at highly correlated variables, and it's going to make one of those coefficients shrink and be really close to zero, in a way that is kind of removing one of those for you and keeping only the other one. And with that is basically kind of doing some variable selection for you already and avoiding multicollinearity at the same time. And so the coefficients of unimportant and or correlated variables get shrinked, get constrained in a way that they have very little impact on the model, and only variables that have a higher impact are allowed to have their coefficients the number that they should be if you just run a regular regression. So we need to apply some type of penalty, some type of penalization to that function that minimizes the sum of the squares of the error. So we can identify these variables and shrink their coefficients so they don't have an influence. There are two main types of penalties and penalization types. One of them is called ridge, so ridge regression, if you're familiar with that or heard of it. The other one is called lasso. And the other one, which is a combination of both ridge and lasso, is called elastic net or ENet. So we're going to talk about the theory of ridge, lasso, and elastic net. But for today's actual coding exercise, we're going to train an elastic net because it is a combination of both ridge and lasso. So it would be the most complex of the three. All right, so let's talk about penalties now, starting with the ridge penalty. So ridge regression is applying a ridge penalty. So the size of this penalty, which is also referred as L2 norm, can take a wide range of values, which are going to be controlled by the tuning parameter lambda. Keep this in mind, tuning parameter lambda, right? So we have something that we have to tune. We have a parameter we have to optimize. We don't know what's the best value for any given data set. What happens behind the scenes when you're running a ridge regression, applying a ridge penalty, is it looks exactly the same way as the linear regression we were talking about before. So the model will look the same. So strength explained by all these 72 other variables. But on the function that's minimizing the distance between the points in the line, there is this extra term here, L2, the penalty. In this case, the ridge penalty. And really what this is doing is this formula here. So on the code, okay, there we go. So what L2 is just the sum of all the betas. So the betas would be the coefficients for each one of those variables squared, but multiplied by lambda. And again, this is the number that we are looking for. What is the best value for our data? So this is the actual penalty that is being applied through the L2 penalty here, minimizing both the error, but with this penalty L2. So if lambda is equal to 0, then this whole term here goes to 0, meaning that this is 0, meaning that the function is actually the same as would be an ordinary least squares, which is what we do by default when we run regression. And then as the value of lambda increases, and again, the value of lambda is something we have to find. We don't have a good answer for it before we train the model. But as we start increasing the lambda from 0 towards positive infinity, this penalty becomes larger and is going to force coefficients of some of these variables towards 0. However, not all the way. It's not going to completely set the coefficient to 0. It's going to get really close to 0 and stay there. And that's important because that's going to be a distinction between ridge and lasso, as we're going to see in a moment. So I have here a figure that exemplifies that. So here, imagine that you have a model that we have, let's see here, 5 predictor variables. So we have a y variable explained by 5 predictor variables, 5 x's, which are the lines we're seeing here. And we have here the coefficients of those variables. So imagine you have, strength explained by precipitation, solar radiation, Tmax, Tmin, vapor pressure, 5 variables, right? Each one of those variables gets a coefficient in this regression. Those coefficients are what we're seeing on the y-axis. On the x-axis here is lambda. So is the value that this hyperparameter takes in this example. As I hope you can see here, the greater the lambda value is, these coefficients start being pushed towards 0. So this on the y-axis, this is 0. So these coefficients start being pushed towards 0. They never become fully 0, but they start being pushed towards 0. And the ones that are pushed first, so I guess here we can see x2 perhaps is the first one that goes near 0, and then x5 and 3, and then we have x1 and x4. That order, I guess, of how early, like at the lowest lambda values that they get towards 0, those variables are going to be either least important or going to be the most correlated with another variable. So this is what ridge regression is doing for us. Imagine in our case, we're going to have 72 lines here, one for each one of the weather variables. So as we increase the number of the lambda value, more of these variables are going to have their regression coefficients being pushed towards 0, meaning that they're going to have a less effect on the actual regression model. And they're going to also, this is happening in a way that is finding, so the way that the math works behind the scenes is that it's already looking for those multicollinear variables and pushing one of them towards 0 and not the other. Of course, if you have a very strong lambda value, all variables are going to be pushed close to 0. So our goal here as data analysts is to find a lambda value. So imagine that we train a model and determine, well, lambda here should be 10. So if we keep 10, we see that variables 2, 5, and 3 are already moving a little bit towards 0. They're not completely close to 0, but they're already moving. And then we see maybe that x1 here is the one that's farther away from 0, right? So it's doing that variable selection for you already. However, it is our job to find what is the best lambda value for your data. This is going to be data specific. So it's not like, well, there's a magic lambda number that works for every model. We have to find that number. Now, one characteristic of ridge regression is that it does not fully perform variable selection because it never sets any coefficient completely to zero. They may be really close to zero, but they are never zero, meaning that in the end, a ridge regression model will still have all of your X predictors in the model. It's just that some of them are going to be, the coefficient is going to be really close to zero and others not. So, if in your case, if you wish that is, so if that's what you want to do, you think that all these variables are important, you're just trying to assess, allow some of them to have a larger impact in the model than others, but you still want to have a model that has all these variables, then ridge regression is the way to go. Because it's still going to keep all those variables, just going to have some of the coefficients really close to zero, while others will not. However, in some cases, we may want to actually set some of these variables to a zero coefficient, so it's a little bit easier to interpret, right? So imagine that out of the 72 other variables, perhaps there's only, I don't know, 25 of those original variables that will have a higher impact on fiber strength, and I just want to keep those and look at the coefficients of those variables to be able to interpret what this model is doing behind the scenes. So if that is what we want, then we're going to have to look into a different type of penalty, which is going to be the next one we're going to talk about, that is called lasso penalty. So the lasso penalty here, it works very, very similar to the ridge. The only difference is on the penalization type and how that is specified. So the lasso penalty, so lasso stands for least absolute shrinkage and selection operator, but I guess most people just refer it to lasso. It is an alternative to ridge, and the difference is very small, and I'll show you that in a second here. And with lasso, we're applying a L1 norm type of penalization, whereas on ridge, we're applying an L2 norm penalization. So another way of seeing that is that in this case, lasso penalty, again, the only difference, if you think of a linear regression model without any penalty, so a regular regression model, and a lasso model, is that you have this L1 penalty when you're minimizing the sum of squares of the error. And what L1 is basically this. So it's also a lambda value. There's also a sum here. The difference between lasso and ridge penalty is how the beta j's, how the coefficients of those variables are treated. In the case of lasso or L1 normalization, you're taking the absolute value of the beta j's, of the coefficients. Whereas with L1, you are taking the square, or not the square root, but you're taking the coefficients to the power of 2. So if you go back, oops. You're taking the square of the coefficients on the L2 normalization on the ridge regression. On the lasso regression, we're taking the absolute value and not the square. That is mathematically the only difference between a ridge and a lasso regression. The consequence of this is that lasso is actually going to push some of those variables to be completely zero, to have a coefficient that's equal to zero, whereas ridge does not do that for you. So lasso would do that for you. And this is an example, a very similar example as what we were seeing before. So we still have our 5x variables predictors in this model. We have a lambda on the y-axis that we are training here. So going from low to high lambda, and we're seeing that some as they start shrinking the coefficient of some of these variables, they get completely equal to zero. You can see that they really touch that zero intercept here. So it is doing fully variable selection for you. So a ridge regression, the first one we talked about, the output of that is going to give you still a coefficient for each one of the variables. It's just some of them are going to be very small, whereas others are going to be large. With lasso regression, which is what we're seeing here, you will get only coefficients for the variables that were not pushed towards zero. So it's going to get less coefficients in the end of training a lasso model, because some of those coefficients were set to completely equal to zero. Those variables get dropped from the regression model. So lasso penalty, it improves model fit while also conducting automated feature selection for you. So lasso is one of the model options that will do feature selection for you. All right, so that was ridge and lasso regression. I want to take a quick moment here and ask if anyone has any questions or need clarification on anything.
The assumptions of linearity.
So what assumption of linearity?
I don't know, like for any linear model, we wanted to accomplish the four assumptions. We've been always checking.
They would still apply, right? So we would still, and that's a good point because I don't think I included code to check the assumptions, but I will in the future. But yeah, so we should still, because it's still a linear model, right? So we still want to check the assumptions and make sure they're being met. I have not done that here. And but it's definitely something, it's really is interesting to some extent because in machine learning modeling, even though we're using linear models, I mean, really a lot of machine learning algorithms are just different ways of combining linear models, right? Linear model is really the backbone of a lot of the machine learning algorithms, including what we're seeing here. But you don't see as commonly in the literature people checking assumptions of machine learning models. And I don't know if I have a good explanation for that. Perhaps that happens because you are checking your model quality by doing the resampling and doing different model fits and checking R-squared and RMSE. But still, you know, they will still be prone to suffer from all, if you're breaking the assumptions of their model, they're still going to be prone to that. But maybe because you have here the option of trying many different models and options and hyperparameter values, maybe that would be the reason why it's not as prominent in the machine learning examples and literature to see, like, for people to say, I train a machine learning model and I check for assumptions. Like, it's difficult to see that in the literature. However, when you're thinking about experimental design data, that is like that's a must, right? You have to say it because you don't have anywhere to go, right? I mean, I guess you have, like, you could, you know, do repeated measures or other things that we have not gone through in the class to improve a model, but you would not be fitting tons, like thousands of models to the data to find the best in an experimental design setup, right? But yeah, but you're right. I mean, the same assumptions still apply here. Perhaps the assumption is just that we're judging models more based on the predictive ability rather than assumption being violated or not. So perhaps a model that violates the assumptions would be a poor predictive model. Perhaps that would be the reason there. But yeah, it's definitely, they're still prone to all the assumptions and breaking the assumptions as well. Awesome. Yeah.
As you said that it will only keep those residual values that will be like close to zero, it will push it towards zero. Like it will try to squeeze all the data. But won't it be like a biased analysis? Because in real life data, we will have like 1 kg yield and we will have 100 kg yield. So like it will discard all the 100 kg ones or like above 50 and just keep the ones close to zero.
Okay, so here's where I think maybe maybe I wasn't clear. So we're not changing the data, right? So the data points are still going to be there exactly as they are, right? So the data is not what is changing. Because here, so in this example here, it's a very simple model where we have like sale price explained by live area, right? So it's a very simple model. It's easy to visualize this relationship here. But now imagine a model that we have sale price, but then you have 72 x's, right? It's really difficult for us to even think of how all those lines would be intersecting and playing a role in the model fit. But imagine that if in this very simple example here, if living area was highly correlated with something else, that if you plotted the line of that other variable, it would be really like on top of this regression line. So the coefficients would be the same. Now, what the model is doing is not changing the data, but is forcing one of these coefficients towards zero. So we only keep the other one. Yeah, so it's the coefficient associated with the predictor variable and not the data that's being shrunk. So, if you think of it like this is probably, so if we had the mathematical equation of this model, it may be something, I mean, I'm just gonna make something up. Let's say sale price equals to 40,000 is the intercept plus, I don't know, let's say 1,000 times living area. So the 1,000 times living area, that 1,000 is the coefficient. That 1,000 is the slope. So it's that 1,000 number that gets shrunk and not any other data points. Any other questions? All right. So let's talk about elastic nets. So elastic net is basically a model that we combine both the ridge and the lasso penalties in the same model structure. So we're basically generalizing both of those into one model, which mathematically we'll be minimizing the standard error, or I'm sorry, the sum of the squares of the error plus the L2 norm, which comes from the ridge regression, plus the L1 norm, which comes from the lasso regression. So we're bringing both of those penalties here in the same algorithm to minimize the sum of the squares of the error. So why would we do that? Why would we want to combine both of these penalties into the same model? So even though lasso models will do feature selection for you, but when they have two very strongly correlated features, they push one of them towards zero, but the choice of which one is pushed to zero is somewhat arbitrary within lasso. And so it's not a very systematic approach when you're just considering lasso. In contrast, ridge regression, the penalty that we use for ridge regression is going to be more effective in systematically handling those correlated features. And to tell the truth, I don't necessarily know how this happens behind the scenes, like why mathematically ridge is more systematically in bringing one of those correlated variables closer to zero. But the theory says so, and because I'm not a mathematician, I'm not showing any proofs. So I guess, we're trusting that advice that ridge regression is doing a more systematic approach to select multicollinear variables or to select one of a multicollinear pair, whereas lasso doesn't do that in such a systematic way. So bringing both of these penalties together gives the advent on an elastic net model, gives the advantage of both enabling effective regularization. So bringing multicollinear variables, unimportant variables close to zero, which happens from ridge, but ridge doesn't set them completely to zero. So ridge doesn't do feature selection, which is what lasso brings into the equation. So ridge is better to identifying the most important features, but it still keeps all of them. And lasso takes those features identified by ridge and then sets them to zero, right? So bringing them together gives us that benefit. And this would be a model or the output that we would have from a elastic net output. So we see here that the variables are being pushed towards zero because of the ridge penalty. And then lasso takes those really close to zero and set them to zero collapse. Just looking at this plot, it looks very similar to the lasso one, but it is coming from an elastic net model that implements both penalties. All right, so this is where we're going to start coding. So you already installed tidymodels. If you were successful in doing that, do not run this piece of code because that's going to start all over again. You don't want that to happen. But also, when I ask you to install the package glmnet, so you can just uncomment, run just a line of code, and then comment again or delete the line afterwards. And also the package VIP for variable importance. So glmnet is going to be the package that actually has the functions that we're going to train a elastic net model. And VIP is going to help us to look at some plots of variable importance at the end of the training exercise. So once you install that, make sure you play this chunk so you get these packages loaded in your environment. If you try to load tidymodels and it gives you that rlang version problem, you're just gonna have to do an install.packages rlang, and perhaps you're gonna have, after installing, you may need to restart your session. So coming on session and then restart R. I am unable to install tidymodels. Austin, do you want to share why?
Sorry, I was typing that as you were saying what to do, so I was a little behind. So I'll try what you were just suggesting.
Okay, well, so when you, I guess, are you having the issue when you try to install or when you try to
I
load?
installed it proper. It said no, when I installed it said error. Like when I go to like restart session, click yes, and then in my console it would say error. And then but eventually like like I said, it gives you the option yes or no. Every time I'd click yes, it would in my console would say error, and then would try to do it again. Eventually, I said let me click no and see what happens, and it looked like it would go through. But and when I go for the library, it's error package or name failed tidy model. Like it's an error now in the library, and I can't install it.
Is that saying that rlang is not like a different version of rlang is trying to be when you run library tidymodels? Does it say anything about rlang?
No, sir, I don't see it. I'll type my error right here.
Okay, so in your case, it's asking for a CLI package, which I did not have happen on my side. But the way that I would fix this is, so it looks like, so maybe you can try to do an install packages CLI. If it says like package already loaded, want to restart, you can say no, see what happens. If you're able to install the package CLI, then I would restart the R session and then I would try to load again, but make sure then you delete that install packages so it doesn't.
Can you tell me that the last part again? Because I'm getting the message that says one or more packages to be updated are currently loaded. Restarting R prior to installing is highly recommended. Yes or no?
You can say no.
Okay.
And then tell me what happens.
Yes, sir.
So while that's going for you, Austin, anyone else is still having issues installing tidymodels or loading tidymodels? So we're gonna know if it was successful if you try to run library tidymodels, and if you get an error, then something went wrong. If it doesn't say anything, then it worked all right. You're good.
It looks like it installed package correctly, but I'm getting the same error.
Okay, so you ran the install.packages CLI,
Yes, sir. Yes, sir.
and did you try to then go on session and restart R?
So restart R after I've installed the install package.
Yeah.
Okay, I'll try that.
So restart R and then try to load tidymodels again.
So, same error.
Okay, so I'm not sure what is going on there, and since it doesn't seem like anyone else is having a lot of trouble, is it okay if we just keep going? I help you afterwards. So
Yes, sir. I'm gonna keep playing with it, see if I can figure it out.
yeah, I mean, you're gonna be able to run some of the code, but it's gonna get to a point that's going to require tidymodels functions, and at that point,
Sir.
you're not gonna be able to run. But if you still wanna, copy or just follow along, I think it's still gonna be very valuable.
Yes, sir. Thank you.
All right. Okay, so let's keep moving here. So the first thing or the second thing I guess we're doing is bringing the data, which again is that weather month sum.csv. I left you the code there so you don't have to do anything with it. Just I guess you just have to run it. What's up? So we run it, it appears in our environment. If you remember, this data set has the 698 observations because it has 698 site years that we had in the original data set, and it has 75 columns. That is year, site, fiber strength in grams per text, and then all of our weather summarized variables that we already pulled from open source data, DayMat, process them, wrangle them, and export it. So this is the data we're going to use to train the model. So again, the goal is to train a model to predict fiber strength in grams per text using these variables in an elastic net framework. Okay, so in the lecture, we talked about this workflow, and that workflow can be applied with any programming language, even within a given programming language with different packages. The way that I want to teach you how to train a machine learning model is going to be to apply those concepts, but to use a family of packages called tidymodels. I am a big fan of tidyverse, so using ggplot, dplyr, tidyr, other packages. So using the map functions with per, a lot of those functions are all tidyverse related functions, right? They all follow a similar syntax, a similar philosophy of how you code them. Tidymodels is that, but for machine learning training in R. So the name tidymodels itself doesn't have any functions on its own, but it is a family of packages. So I'm just going to copy here this URL and show you the page for tidymodels. They have great documentation for many different machine learning models. So anytime you want to train a machine learning model in R, you can refer to this resource. But so tidymodels is a family of packages where it includes rsample, which is going to be a package that help us to do data split and resampling, as we already talked about those topics in the lecture. Parsnip is going to help us to have a unified interface to different machine learning models. What happens is different machine learning models and the implementation of those models in R were developed by different people. So if you're on a random forest, it's going to be a completely different way of specifying the model, the parameters, and so on, than running ElasticNet, than running any other machine learning model. So Parsnip is a package that gives you a unified interface. So the way that you specify your models, regardless of the model, is going to be very similar. And behind the scenes, it has all these differences in the packages, and it takes care of that for you. So you don't have to think specifically for each package, for each algorithm that you're training. Recipes is a package. So all these are packages in tidymodels, right? So rsample, parsnip. Recipes is going to help us to do automate, or to, I guess the word is portable data pre-processing. We're going to see what that means in a second. Workflows is a package that combines a lot of these components into a workflow. I'm not going to show you how to use a workflow. So let me make sure I don't get you confused. I'm showing you a workflow that works here for machine learning. I'm not going to show you how to use the package workflow because I think it adds a little bit more complexity for a good reason, but we can do it without that package. So for this exercise, I'm not introducing this package workflow. The tune package is going to help us to fine tune hyperparameters and how to do that process. You're going to see that in a moment. After we do that, yardstick package is going to help us to assess metrics. So evaluate a package with R-square or MSE or really any other metric. The broom package we have already used before. It just helps us to get predicted values for your model. And then the dials package helps us with the grid search type of things. So you can see that, when they were developing these packages, they developed packages very specific to each step of a machine learning workflow to keep them simpler and also efficient. So tidymodels is just all these packages here being loaded at once. And here's just a little bit more about each one of those packages, and it's just what I just told you in words. All right, so starting with our machine learning training, the first step is the pre-processing, right? So the pre-processing is where we do two things. One is data splits. The other one is going to be the pre-processing of the data itself. So let's come here to our first chunk that I'm calling weather splits. My goal is to take our 698 observations, have 70% of them into our training data, 30% into our testing data. I'm leaving you here a set seed. So if you remember, in our set seed just determines the position on the random number generator for you. So every time you run something that's random, if you set seed first, it will be random but reproducible. So you can always start on the same position of the random number generator behind the scenes and always get the same outputs, because we're taking 70% training, 30% testing at random, right? So to keep that randomness reproducible, we set seed first. So we're gonna so make sure you run the set seed. So it sets the seed for you, and your results will be reproducible. If you reopen the script and rerun again, and also what I see on my side is gonna be exactly the same as what you see on your side. If we don't set seed, we're all gonna get different data falling to training and testing. So to do this split here, using tidymodels approach, we're gonna assign that to this object called weather splits. The name of the function is called initial split, that comes from the R sample package, where we give the data that we want to split, which is called weather. And then it has an argument for how much you want on training, which is called prop. So prop is the name of that argument. I want to say 0.7. If you run that and then you print weather split, it just used the data that you had, but behind the scenes, it just set these numbers. So the total number of observations is 698, with 210 falling to the testing set, 488 falling to the training set, right? So it just allocated, but it's not showing us yet which observations are where. So that's what we're gonna do next. So come on the next chunk here, I want to basically pull the training data from that initial split, and I want to assign that to an object called weather train. So give the assignment symbol. To pull that training data, there's a function called training, also coming from the R sample package, and we just give the weather split object. So that split object we just created above. If you run weather train and you print it, you're gonna actually see all the rows that ended up in weather train. So 488 rows, 70% of our data, all columns. Now, why is setting seed important? So remember here, maybe just the first one, 1982 El Paso, Texas. If I come here and I do not run set seed again, I just run my initial split again, it's gonna be a completely different set of observations. So if you want your code to be reproducible, you need to make sure that you do random allocation, but you can repeat that random allocation as well. So set seed, I run again, I'll get El Paso, that's the first one, right? So we're just making sure that we're being reproducible here. All right, so we have our weather set, our train set, which is right here. Now we're going to do the same thing with our test set. So we come to weather test, give the assignment symbol. The function here is going to be called testing. So testing, and then we give the weather split. So we're pulling the data from weather split that fell into the testing set. If you run that and you print it, you should have 210 observations, and you should be the same ones as I'm getting because again of that set seed. All right, so if you remember, now we basically completely ignore the test set until the end. We're not gonna touch the test set until we're ready to check our final model predictive ability. So now we take the train set, and that's what we're gonna use to train our machine learning model, which is what we're gonna do next here. Well, I guess we have a data processing step before we do the training. Okay, so before training, we need to perform some processing steps. So for example, we could, in this case here, for regression, it's going to be important to normalize our variables. So have them centered at 0 and have a standard deviation of 1. We could remove unimportant variables in some way, and we're going to do that. I'm going to show you how to do that. We could drop NAs if we had them. We could also perform PCA on the go and work with the PCA scores instead of the variables. We could remove columns that only have a single value. So let's say you get this data frame from someone and you have one column that says, I don't know, maybe it's like university and it's UGA all the way down. There's no reason for you to keep that column in your training because it makes no sense, right? So you could easily remove columns that have a single value all the way down. And really a lot of other options. So what we're going to do here is create a pre-processing recipe. And this, again, is a language that's used by tidymodels. You may not have heard or will hear this in other frameworks of training machine learning models, but this is how they refer to it. So this recipe that we're going to create, given these processing steps, we're going then to apply that to the training data and then start training the training data after it has received that recipe that we're going to create. The reason why tidymodels have this idea of a recipe is because, so we're going to have this recipe that will first apply to the training data, but then all these steps that we processed will also be needed to be applied to the test data when we train it. So imagine you take the training data and you normalize it. So we have variable center is 0 with standard deviation of 1. You create a model that's based on normalized variables. Then you get to your test set, and your test set has not been normalized. So they're not on the same scale. So we're not going to be able to easily, assess your model quality on tests because train and test, one is normalized, one is not. So by creating a recipe, it's really easy then to apply this recipe to the test sets or even to other data sets that you want to apply once you create a recipe. What we're going to do is just use two recipe steps, which are going to be to normalize variables and to remove unimportant variables. But there is a huge list of steps you can create in recipes, and I left you the code here in case you want to explore on your own. All right, so let's come to the next chunk and let's create our recipe right here. So you can give it the assignment symbol. The first thing, so if you come after that first comment, is we need to define the structure of our recipe. We're going to use this function called recipe, where we're going to say the name of our variable here, our predicted variable of strength. So strength underscore gtext explained by, if I want to explain by everything, all the columns I have in a data set, there is an easy shortcut for that, which is just adding a dot. So that dot means that it is taking all the other variables on that data frame. And then I give it a comma and I need to say what is the data that I want to apply this recipe. So data is going to be equals to weather train. So notice how the recipe we create is going to be applied to the training data only. All right, so if you just run that and you print it, this is what it says. It's a recipe that has inputs, 1 outcome and 74 predictors. It knows what is the outcome, what's the predictor, because of this formula here. This is the outcome, everything else are predictors. So we establish our recipe, or the beginning of our recipe. Now we need to add steps to this recipe. So the first step that I want to do here, if you just add a pipe, is I want to remove year, site, and also some variables here that I'll tell you in a moment. If you just want to uncomment, I left you all the function there. You can just uncomment that step _rm. And for now, I want you to comment the pipe right after that so we can run it and see what that does. So my goal here is to remove year and site because I don't want to allow a model to train year and site. I want that year and site signal to come through the weather variables, right? If I give year and site here, the most important variable is going to be year and site. So they're going to say, well, in El Paso, Texas, it has a different slope for whatever reason, and it gives you a very good model, but a high R-square of a model, but it is based on a site. That is not really our goal. Our goal is to say, if I don't know what site, what year this is coming, can I use weather variables to characterize the site in that year and therefore understand the weather impacts? So I want to remove year and site. And also I'm using this function here, matches, to say any column that I have in this data set that has the words January or Feb or Jan, Feb, Mar, APR, Nov, or December, I am removing them. That is a decision I'm making as a data analyst because if you think of it, cotton for the most part is planted around May and harvested around October. So why would I allow a variable in December to tell me that it has an effect on fiber strength if fiber strength has already been harvested or fiber has already been harvested by that time of the year? It doesn't make sense. And also, if you remember, some of the multicollinear variables were like in those months very close by. So just making sure I remove those variables. So every variable in my data set that has these words in their title are going to be removed because I'm using a step underscore RM, which removes variables. So if you run until here and you print your recipe, now it's going to see, it has an operation here where variables removed, year and site, and then it has ... because there are many others potential variables. Now, the last step that I want to apply here is to normalize these variables so they have a mean 0 and standard deviation of 1. That is important, especially when you're applying a penalty regression like we're doing, because if you allow the variables, if you don't normalize the variables, you allow them to have their coefficients are going to be larger if the variable unit is large. So again, imagine if you have day length in seconds that has a value of like 48,000, and then you have mean temperature in January that has a value of 10. So mean length is already having a very large coefficient because the magnitude of the variable is larger. And we don't want to allow for that to happen here. We want all of them to have the same scale. So then we need to normalize them. If you remove that pipe there and you come after this comment, we're going to use a function called step underscore normalize. Now we need to tell what do we want to normalize, what we do not want to normalize. So I want to normalize all numeric variables in this data frame. So there's a function, helper function that is, you can say all underscore numeric, that's coming from the recipes package. However, I do not want to normalize our predicted variable, which is strength. For me to just make sure that we don't normalize that variable, I can just come here and say minus, and then there is this option for all underscore outcomes. So I'm basically saying that I want to normalize everything that's numeric except my outcome variable, which it knows what is my outcome variable because of this formula here. It knows that this is my outcome variable. So if you just run all that recipe and you print it, this is the recipe, right? So I have one outcome, 74 predictors. I am going to then remove some of those predictors and then scale, center and scale all numeric except all outcomes. So we have this recipe. We have not applied the recipe yet. We just set up the steps. So the next step now is for us to prep this recipe or to apply this recipe to the training data. If you come here on the next chunk, we're gonna call this recipe. So weather underscore recipe. Plug in a pipe and call this function prep, which also comes from the recipes package. If we do that and you print this object, now is going to tell us that, so training information, training contained 488 data points, no incomplete rows, so there's no NAs. Then it's saying here variables removed were year, site, and a lot others. And then it's centering and scaling for all of these variables here, which were all the numerical ones that were still left. So if you notice here, there is no variable that was in January, February, March, October, November, October, November, and December are just the other ones because we did that step on the recipe. All right, so So we did our data split between training and test. We created a recipe to pre-process our train data, and now we're going to start training on that pre-process split training data. One thing to keep in mind is some of these processing steps, you could you could do some, perhaps most of them, with just dplyr data wrangling functions. If you do them instead using a recipe, that's gonna help us to make, again, your recipe portable. You can easily apply this recipe to other data sets like we're gonna do on the test at the end. So when you're training machine learning models, that is what a recipe does for you that just a regular dplyr pipe flow would not. Okay. So again, now we're getting into the training part of the exercise. And the first thing we have to do here is specify the model that we're going to use. For that, we need to specify the type of model. So this would be, is it elastic net? Is it just a lasso? Just ridge? Is it random forest? Whatever it is, that's what I mean when I say the type of model. And then we need to specify what engine we want to use. The meaning of engine is because in R, and I'm sure in Python and other languages, you have different packages that can do the same task for you. So in R, I think there's maybe 3 or 4 packages that can do elastic net for you. We need to specify which of the packages, or in other words, which of the engines we want to use in this exercise. So type of model and engine. All right, so another thing before we specify the model is that elastic net has 2 hyperparameters that we need to determine. One is going to be the penalty, which is basically our lambda, and the other one is the mixture. So mixture is going to range from a value of 0 to 1, where if you have mixture equals to 0, then that penalty is basically just a penalty that would come from a ridge regression. If we have mixture equals to 1, then the penalty is going to be the same as what would be applied to a purely lasso regression. Our goal here is to find 2 things. One, penalty, which again is equivalent to lambda, and then the mixture, which is a proportion between 0 and 1 that is going to tell us how much of weight is going to be given towards lasso or towards ridge. So those are the 2 hyperparameters we have to fine tune. All right, so if you come here to the next chunk, that's what we're going to do. So we're going to assign this to this object called enet spec. If you come after this comment here, we're specifying linear regression as our model type, asking to tune the hyperparameters. What we're going to do right here is call a function called linear_reg. This function comes from the package parsnip. So remember, parsnip helps us to have a unified framework to specify models. In here, we're going to call both of those parameters. So penalty is one of them. I could, I want to tell you here, I just want to put a number of 10 here. And then give it a comma. The next hyperparameter that we'll fine tune is called mixture. And let's say I want a mixture of 0.4. If we just run that and we print this object, it's going to specify for us that is a linear regression with main arguments of penalty equals 10, mixture equals 0.4, and the computational engine that's going to use is linear model. So right now it's running an LM function. I do want to use a different engine, a different package. So let's change here the engine. I want to give it a pipe. If you come after that, it specified the engine comments. We're going to use here a set_engine function coming again from parsnip. And within quotation marks, let's give it a value of glm net. So again, I'm saying here that I want the package to be used to train this model to be the functions from package glm net behind the scenes. So if you run that and you print it, now we change the function or change the engine for us. If we keep going with this model specification here, so the enet spec, what it will do for us is is going to fit a elastic net model with penalty equals to 10, mixture equals to 0.4. So if we keep going this way, it is not fine tuning, it's not optimizing any hyperparameters because you're given it a fixed value. For us to tell the engine or to tell the model specification that we want to fine tune these values, instead of giving a given number here, we just come and say tune. So tune is a function from the tune package that we're just telling this setup here that I don't know the value here. I want to find the best value for this data. So if you change that to tune and you run it, now you're going to see that the main arguments don't have a value. They just have a tune function right there, meaning that these values will be found through the training of the model. So right now we don't know what they are. All right. So for us to tune those hyperparameters, if you remember from class, we have to create a grid, right? So we talked in class about a grid search, which you define a fixed grid, and then a iterative search. I want to show you today the grid search first, because it's perhaps the first step into machine learning is using grid search, and then the iterative searches are more complex. We may see that in future exercises. So I left you here all the code, but really what I'm doing is I'm getting a sequence from 0 to 100 by every 10. So if you just run that seq function, we're going to get 0, 10, 20, and so on, and assigning that to penalty. And then I'm getting a sequence from 0 to 1 by every 0.2. So 0, 0.2, 0.4, all the way to 1, and assigning this to mixture. And I'm plugging that inside of this function crossing. What crossing does for you is that it creates all possible combinations of all levels of penalty and all levels of mixture. If you just go ahead and run this and you print eNet grid, this is what we have. We have a data frame with 66 rows, which each row is one potential combination of the levels of penalty and the levels of mixture. So if you think about it, why do we have 66? Is because here, I think we have 10. So this sequence here, the unique values of penalty are 10 levels. So I'm trying to just run this. So this has length 10. This has length, oh, this is not 10, this is more than that. But anyways, if you multiply 11 by 6, I believe. So that's why you get 66, is just all combinations between all of these hyperparameters, values of penalty and mixture. All right, if you remember in class, we saw a plot of an example of a plot where you had a fixed grid, right? You have parameter 1 on the x-axis, parameter 2 on the y-axis, and a grid with points where those values fell. I do want to make a plot here so we visualize our grid and we understand what's going to be happening at the end. So if you come on this next chunk, let's start a ggplot where I want to say data equals the object that we just created above, which is called eNet underscore grid. Give it a comma. On the AES, I want to put on the x-axis, I want to have mixture. On the y-axis, I want to have penalty. And then if you just come out of that ggplot, add a plus at the end, I just want to call for a geom point so we can visually assess this grid. Let me just give a moment here so you all catch up. So this is what we're seeing. For each one of the points that are intersecting a given mixture and penalty value, we're going to be training models at each one of those points and identifying what model gives us the best predictive ability. So this is our fixed grid search that we're going to be performing here. All right, so for us to actually implement the search on this grid, we need 4 things. So one is our model specification, which we already have on this object called eNet spec. We need the recipe to process the data. We have the recipe on the object called weather recipe. We need the grid, which is what we just created above on the eNet grid object. But if you recall, from that, we have that schematics of like all data being split into train and test, and then the train, we do resampling, like some type of cross-validation on the training set to find the best number or the best values of hyperparameters. We have not established our resampling strategy yet. So let's do that in the next chunk, and then we're gonna be able to actually apply our grid search. So there are different resampling strategies. If you go on the documentation of our samples package, you're gonna find, I don't know how many options there. I do want to implement the one we talked about in class, which is the V-fold cross-validation. So if you remember, we're gonna define, in this case here, I want to define V as 5. So we're gonna have 5 folds. So imagine that all of our training data, which is how many rows again? 400 and some? 488. So each one of those 488 rows are gonna be split into 5 equal size groups. 5 times, right? So imagine 488 and you chop it up into 5 pieces. Now, each one of the folds is gonna use 4 of the pieces to train, 1 of the pieces to test. And then on the next fold, a different piece is used for testing and others are used for training and so on, right? So that's what we're gonna define here in this next chunk. So if you come here and start coding with me, give it the assignment symbol, there's a function called vfold underscore CV coming from the R sample package as well, where we give the data that we want to fold, which is, which one? The train, right? So the training data. So weather underscore train is what we want to apply the folds. And then it has the argument called V for how many folds you want to do. I want to do 5 folds. So if you run that and you print the resampling fold CV, this is what we get. We get a nested data set with a column called splits, a column called ID, and on the splits column, you can see that this is like a nested data frame as we've been seeing already when we're doing iteration. So I want to explore one of those folds. So I want to open up this first fold here for us to look into it. So I'm just going to copy the object name. I'm going to use the $sign splits, and I want to use the bracket, double bracket notation to pull that first fold. If I run that, it's telling me here that it has a total of 488 observations, like we expected, and it's using 390 of them to do the analysis, and then 98 to do the assessment. So if you remember from the workflow we saw in class, we had again all data, training, testing. On the training, we do the folds, where each one of the fold have an analysis and an assessment set. So that's what's happening behind the scenes here. If you change this 1 to 2, so we pull the second fold instead of the first one, you're gonna have the same number of observations in analysis and assessment. The difference that we're not seeing yet is that which observations are in assessment and analysis are different from across different folds. Yes.
Is it same for all folds, the number of training?
So they should be very close to being the same. Sometimes, like, let's say if you think of like, if you have 488 observations, if you split that in 3 or 4 or 5, there's gonna be a point where maybe you're gonna have 1 or 2 observations more in one of the folds. But overall, we're gonna try to balance that the same. And we can actually try that out. So yeah, so the fold 4 has a little bit of a difference. And 5 as well, yeah. So it may be a little bit different, but for the most part, it's gonna try to make that the most even possible. Bfold should be doing on weather recipe or weather train. So it should be weather train, Sikar, yeah. So the recipe itself is gonna come into play in the next step. Yeah. All right, so now that we have our 4 components here to do the grid search, which was to have a model specification where we set linear regression and set the engine. We had the recipe with the pre-processing steps. We had the grid identified above, and we had the resampling strategy. We can actually apply the grid search. So if you come here on the next chunk, we're gonna call a function called tune underscore grid, coming from the tune package, where the first thing that we're gonna give it is the actual model specification. So enet underscore spec. If I just run that for you to remember what that is. It's just that specification saying that we want to tune penalty and mixture. And this is where that comes into play. It's going to know what to tune because in the specification, we included that tune function there. You can give it a comma. It's going to have a preprocessor argument. So this is going to be the recipe. So Sakura, this is where we give the recipe that's going to be used, which is the object weather underscore recipe. We can give it a comma. Let me try to squeeze this. The next argument is called grid. So that's where we give the object that has the actual grid, which we created above, and it's called enet underscore grid. And then lastly, it has an argument called resamples, which is where you specify the resampling strategy, which we just did above. And the name of the object is resampling underscore fold CV. So let's go ahead and run this. It may take a quick moment, depending on the model, depending on your grid type, depending on the grid function you're using. It may take longer. In our case here, it doesn't take a lot long. And it's giving a warning. You probably got the warning as well. It's just saying that for some of the folds, it was not able to, so for some of the folds and some of the hyperparameter values that we're trying, it was not able to fit the model. That's basically what it's saying. If we print this object here, enet grid results, this is what we have. So for each one of the folds, we have metrics and we have notes as well. What I want to do here is just pull up this first metric here. So we can see what's in it. So if you just call enet grid result $.metrics bracket 1 to pull that first cell there. This is what we have in that first cell. So for that first fold, it tried all combinations of penalty and mixture. And then it has a metric column that is saying RMSE. If we keep going here, the next one is R square. It's just telling us what type of estimator you used. I think this column here is all the same value across. And then it's giving an estimate. So if this estimate here is for RMSE, this is RMSE. If on the metric column you have R square, this is R square. And then it has, I think that those are the most important pieces. So what you're seeing here is that for each one of the folds, it ran 66 models on the analysis set, and then applied that analysis set to the assessment set and calculated what was the R square and the RMSE of that. For each one of the folds, each one of the 66 hyperparameters. So really, it just ran 66 times 5. That's how many models it just ran for you. Right, so it did the grid search for you, and these are the results. Yeah, so there are some, so when we ran this grid search and we got some, the warning, it was because for some of the folds and for some of the combinations of penalty and mixture, it was not able to fit a model. So that's why you get an NA on the estimate. And that's why we got the warning when we ran it. And if you think about it, we have 132 rows here on this, and this is just fold 1, right? We have 132 because we have one row for each combination of the values that we define on the grid, which were a total of 66, times 2 metrics, right? Because we have 66 values for a metric equals R square, 66 values for a metric equals RMSE. And this is just for the first fold. We have this again for all the other 4 folds that we created. All right, so I want to show you here how can we easily pull a summary of these metrics and plot them so we can visually assess what was the best combination of hyperparameter values that optimize either RMSE or R square. I gave you most of the code there. I just have 3 ... on the second row, where I want to bring here, if you delete that, I want to bring here this function called collect metrics. So this function here is coming from, let's see what package. It's coming from workflow sets, which is another package as part of tidyverse. If you just run that, so before you add the connecting pipe, if you just run this is going to give you a summary across all folds, a summary of RMSE and R square for each one of your penalty and mixture values. One thing to notice here is you did get an RMSE and R square value for each fold in each combination of penalty and mixture. When you ask to collect metrics, it is, I think, is giving you the average across all folds. So this is the mean, yeah, I guess it's saying right there. This is the mean RMSE across 5 folds when you train with a penalty of 0 and mixture of 0. Because this is a statistical summary, it also gives you a standard error of that and gives you here n equals 5, again, because you had 5 folds. All right, so now feel free to add the pipe to connect with the following code. We're just filtering the metric RMSE. I'm plugging that into ggplot where I put penalty on the x-axis and the mean, in this case, mean RMSE on the y-axis. And then I'm adding lines and points and coloring them according to mixture. So if you just run that, we can look at this. This is how RMSE behaved for our training process. So I guess let me ask you this first. Are we searching for the highest or lowest value here? What is it that we want out of this plot? Lowest, right? RMSE is the error, so we want a model with low error. So if I were to just visually assess this, the model that is giving me the lowest average error is when I had, so RMSE of just below 2.95, and that's when I set my penalty to 0 and my mixture to 0 as well. That's the model that, and I know that because on the x-axis I have penalty, and each line here is for a different mixture. And very interestingly, at least I think we do have some other lines behind the pink line, but at least distinctively, we can see just the lines for when mixture was 0 and when mixture was 1. Any questions? All right, so I'm going to keep going. So we just assessed our MSC, which is one metric, right? I also want to check R square of these models, which if you come on the next chunk, I left everything for you. The only difference is that we're filtering metric equals R square, but then everything else is the same code. So if you run that, this is what we get. We have, again, penalty on the x-axis, in this case, R square on the y-axis. Interestingly, we see that the best R square we're getting is 0.14. So we're not getting a very strong predictive model out of this exercise anyways. And there are many reasons for that, I guess, you could probably imagine some of them, but the highest potential of the best model we could create out of this is going to have a training set R square of 0.14. And as we increase penalty, we see R square is decreasing. How would you interpret this? If you're increasing penalty, your R square is decreasing. Yeah, I mean, they're going to be to some extent connected, but what is penalty doing?
Number of variables.
Yes, so Neva said, as we increase penalty, we are removing more variables from this model. So our R square is decreasing, right? So that's exactly what's going on here. All right, so looking at both of these plots, I guess we could say that just visually, which we're gonna check these numbers more objectively in a second here, but visually, it seems like a penalty of 0, and because the red line here is mixture, even though there are some points there, and maybe it looks like the pink point, which is mixture of one, is a little bit above the red line, the red dots. So it doesn't have a complete line because when you had a mixture of one, it wasn't able to fit all the penalties. But when it was able to fit, it seems like it has a slightly greater R square than a mixture of zero. But just visually, it seems like potentially mixture of zero, penalty of zero would be the best combination of hyperparameters for us to use in this exercise. So let's go ahead and actually extract those numbers so we get a good understanding of what those values truly are. So if you come here, my goal is to extract the model with the lowest RMSE. So we're going to start with the grid, with that object of the grid result, which is called enet underscore grid underscore result. We're going to give it a pipe, and we're going to call a function called select underscore best, coming from the tune package. And the metric I want to use is going to be equals to RMSE. If you run that and you print that object, is going to give you here, based on your grid search, the model hyperparameter values that created the lowest RMSE on your training set, which again is what we thought it would be: penalty equals zero, mixture equals zero. However, this is based on RMSE. Let's check if the same combination of hyperparameters is what would be recommended if you use a different metric, in this case, R squared. So go on the next chunk, we're going to use the same approach. So we call that object enet underscore grid underscore result, give it a pipe, and we're going to call select best. And now the metric is going to be equals to RSQ, or R squared. We run that and we print it. We actually get a different answer. We see here that is asking for penalty of zero and mixture of one. And really interestingly enough, I'm not sure why, but when I ran this script, when I was developing the script, I got a different answer. I got a mixture of 0.4. So maybe I reran my initial split without setting the seed. Is everyone getting the same answer here?
No.
0 and 0?
I
Yeah,
got
0 and 0.
0. Oh my gosh. Well, I'm guessing there are, yeah, maybe. Wonder what, I mean, we're setting seed, so we're all setting seed. And as long as we're not rerunning functions without, like, running each function once, we should all be in the same position on the seed still. So I'm not sure why this is happening. It should be reproducible.
Two questions. Even my graphs are a bit different. So I was trying to run again because I thought I was missing something. So
Yeah, my graph is also different.
Is a little bit different.
even for R square and for RMSE plots, it's a bit different.
It's a little bit different. So, I mean, definitely this difference is coming from the so there are two randomness components here, right? So the first one is the initial split. The second one is at the V-fold. So there are two random steps in this process. And I thought that setting seed was going to help us to all get to the same answer. Apparently not.
Maybe because of the before they were not evenly distributed. Because
Yeah.
It's divided into 5 equal sets, but it's not evenly distributed.
Yeah, I mean, that would happen regardless. But I think what's happening is we have different observations fall into different folds
What
for
if
some
we
reason.
set seed before the result? Right. before
Yeah,
the
we can do that as well. We can try that. So maybe let's try to do that and just make sure.
I went again and I got the same result.
Yeah, so the thing is, if you don't set seed and even if you just rerun the same function, it's gonna be in a different position on the seeds. So you will get a different result. But maybe if we all set seed right before the grid search, maybe that would make us all get the same results. So for right now, I think that's something that if we have time in the end, I do want to come back and redo it just to make sure that that would happen, that we all get the same results. But for now, I want to keep moving, even if we all get different results on your side. I want to keep moving just so we complete the workflow. And then if we have time, we can revisit this again. All right, so I guess in my case, I would have to make, well, I guess perhaps in your cases as well. I guess the main point here is if I use RMSE as my metric of choice to make a decision of what's the best model, I will be selecting mixture and penalty equal to 0. If I use on my side R square, I would use mixture of 0, penalty of 1. So the two metrics are not agreeing, which could happen. And then in this case, it's going to be up to you as the data analyst, data scientist to make a decision of which one of the two you want to pick. It could happen that both metrics agree, in which case it makes it easier for you. But if they don't, then it's up to you to choose which one you want to select. And of course, if this is a paper, you want to specify that, which metric you use to make your selection of the best combination of values for the hyperparameters. In my case, I wanna use the result when I judge on R square. So if you come here on this next chunk, what we're gonna use is basically just rerun or have a new model specification, new model spec that instead of saying that parameter, that mixture equals to tune and penalty equals to tune, now I have the values that I already found through my grid search. I'm going to specify those values instead. So we come here. If you recall, we called the function linear underscore reg, and we had the penalty argument that we previously said tune. Now we know what the value should be. We're going to specify that. So if I want to base this on the R square, that value is right here on this object best R square $ penalty. So I just specify here best underscore R2 $ penalty. And if I just run best R square $ penalty, I do get the value of 0. I could easily come here and just say 0 if I wanted, but then you have to visually check every time. This is just a way to kind of automate that process so you don't have to make sure you didn't forget to properly change. And then the same thing for mixture. I'm just going to come here and call mixture. That's going to be equal to the best R square model $mixture, which in my case, if I print it, is going to be equal to 1. If in your case is different, that's fine. We just use yours, the value you found, and then if we have time, we can revisit this. All right, so if you run this and you print final spec, it's basically just a model specification that is telling you that penalty. I mean, it's not showing you the actual value, but it's showing you where that's coming from. And we know what they are based on that, on what we just saw on that best R squared object. Okay, so we basically finished training our model. This is the step that we finished training. Congratulations, you just trained your first machine learning model. If that was your first, perhaps it wasn't. And now what we're going to do is validate, right? So remember, now is the time that we take this model and we check how well it does on data that it has not seen yet, which is our test set. In tidymodels, it has this approach of calling a last fit, which is not a type of language you're going to see like across different languages and different approaches to training a machine learning model, even within the same language. In tidymodels, a last fit does two things. So first is going to use the hyperparameters that you found and train them on the entire training set. Because up until this point, that has not happened. Your hyperparameter values were found by training those values on folds, right? On 5 folds in this case. So up until this point, we have not trained a model with those hyperparameters on the entire training set. That has not happened yet. So the last fit does that for you, and then already uses a predict function to predict on your test set by default. So it does 2 steps in one function. It makes life a little bit easier. So let's come here on the chunk called final fit. I want to give it the assignment symbol. We're going to call this function last underscore fit. which comes from the tune package. We're gonna give it the final model specification, which we just created above, called final_spec. We're gonna give it the recipe. Remember, the recipe is portable. So we have to say, how do I want my testing set to be processed before you make a prediction on it? So we give the weather_recipe. And then it has this argument for split, which this is where we give the entire split object. So if you remember, all the way in the beginning, we started with weather, which was our CSV object, and we use the function initial split on that object. And we assign that to an object called weather split. So that was our initial setup of the split. That's what we need to specify here. So that is called weather_split. And the reason why we do this is because our split has information both on the training set and on the test set together, right? If I just run weather split, remember it is that it's specifying how things are being split across training and test. So the split has both training and test in it, which the last fit function knows how to first fit the model, the last model, the final spec model, on the training set only, on the entire training set, and then using the test set to predict, which is R-squared MSE, or the predictive ability of this model should be coming from your test set. So if you run this, and you just print your final fit, it has a column called metrics, predictions. Those are the two most important ones, the metrics and predictions. If we use this function called collect predictions, is basically going to unfold this column for us. So if you run that, you get here 210 rows. Why is that? Why is it giving me 210 rows when I ask to collect predictions?
We have to check these testings.
Because we have 210 observations in the test set, right? So it's giving me the predictions on the testing set, which is important. So it gives me a column called .pred, which are the predictions, and a column called strength GTEX, which is my observed values, the actual measure values. So strength text, observed data, .pred, predicted. All right, so let's check our predictive ability of this model that we trained on the test set. So let's check the metrics on it. So this object that we created here is called final fit. Let's come on final fit. Let's call final fit object, give it a pipe, and ask for a function collect_metrics. Your values may be a little bit different, especially if you had different hyperparameter values on your side. On my side, I'm seeing an RMSE of this model of 2.98 and an R-square of 0.15. So again, not a very large R-square, but again, this data here is across many locations, many years, 40 years in the past, lots of people collecting this data, lots of potential for mistakes. Imagine you have a study across 60 sites, 40 years, and each site had at least one person, which is most likely not the case, probably people changing over time. So a lot of variability coming from this data, just from the data quality part itself. We're also using gridded weather data, which has uncertainties of its own. Also the fact that weather is just one component of any crop response, right? There is also management, there's going to be soil effects, there's going to be a lot of different things that also impact fiber quality in the end. But here we're showing that we're being able to explain 16% of that variability with weather data, which is not, it doesn't look great when you just see it, but if you consider everything that impacts cotton fiber quality and the limitations of data quality, both on the field and the gridded weather, it's not that bad. All right, so these are the metrics on the test set. So if you want to show how good of a model you created and how good of a predictive model you created, this is what you would show. Or two metrics, I guess. You could show other metrics, but based on the test set. What if we do the same on the train sets? So to get a prediction on the train set is a little bit more involved. I'm not gonna go through the code, but basically what I'm doing, I'm not gonna explain to you what the code is doing, but you're gonna have the code if you're gonna try on your side. But I'm using the final spec, fitting that to the train data that I am using the recipe prepared and baking the recipe. This is a function we have not seen yet, but that's how you would apply the recipe. You have a recipe, you prepare, and then you bake it. It's kind of that, baking analogies, I guess. Then we're augmenting. So this is from Broom package to get the predictions, then calculating RMSE, the observed and the predicted values, and then doing the same thing, but then calculating R squared instead of RMSE and just binding those two things into one data frame. You just go ahead and run it. You should run without issues. So let's quickly compare here. There we go. So at least on my side, on top are the metrics on the test set. On the bottom are the metrics on the train set. So this doesn't happen all the time. Sometimes it could be that your model is even better predicting your test set than your training set. It's not impossible for that to happen, but most of the time, your test set is gonna have worse metrics. In my case here, my metrics on the test, it had a higher RMSE. And on the bottom here is on the training. So it had a lower error on the training than on the testing. And it had a lower R square on the, okay, let me make sure I don't get myself confused and I don't confuse you. So on top, we have testing. On bottom, we have training. So training has a lower RMSE than testing, has a higher R square than testing. So the model is a better fit with the training set, which we would expect, right? Because it is seeing the training set. And in this case, it's not like a huge difference, right? So you could report both metrics. You could report RMSE R square for both training and testing. So your audience is aware of what's going on. Sometimes this difference can be larger, even a lot larger, in the sense of doing a way better job on the training than on the testing. There are different reasons for that to happen. But you do want to make sure that when you do your analysis and you write your papers, that if you are providing one set of metrics, provide the one on the testing set. If you're providing both, make sure you specify which one is which. But sometimes people provide one of these sets and is on the training data. And then that leaves you, for prediction purposes, that's not what you want to do. You can provide your RMSE and R square on your training data if you're just trying to explain what's going on with the training data. So we're not creating a predictive model. We're just trying to understand what's going on. It's just inference. That's fine then to report on the training data. But if you're making a model for prediction and you're calling this that you're doing a machine learning model because you want to predict something and you give me a metric on the training set, then you may not know fully what you're doing. All right. Okay, I made some plots here. So again, one very common plot is that predicted by observed plot, right? We want to see how are those two things connected. So that's what we're going to do in this next chunk. I left you most of the code except for a few dotted lines. So I do want you to come along with me here. So starting with the final fit, I want to collect the predictions first. So let's use collect predictions on that first three dotted line or three dots line. If I just run that before connecting, I'm just going to again get the 210 rows with the dot pred being the predictions, the strength g-text being the observed. So I want to connect that pipe now to the ggplot. I guess you would see most of the time people putting the observed data on the x-axis and the predicted data on the y-axis. you may see the opposite as well, but I guess the competition is on the x-axis is gonna have your observed data, which in our case is strength. So strength underscore detects. On the y is your predictions, which in our case are under the dot pred column. If you, let's do this, add a hashtag right before that plus after the geom point, and let's run until geom point only. This is what we see. So observed, predicted, this is what we see. It is very common for people to add a one-to-one line on this plot as well, because the goal here is that you have a good model when your predicted and observed are very close to that one-to-one line. To do that in R, you can come to the last three dotted lines or dotted points there. We're going to use geom underscore AB line. By default, AB line is basically just an intercept and slope line. And by default, the intercept is 0, the slope is 1. So that creates a one-to-one line. I'm also adding a geom smooth of a linear regression to the data points themselves, and just fixing the range of my y and x axis to be within 20 and 40. So if you run all that, this is the plot that we have. We see that perhaps for strength values between, I don't know, 27 and potentially 32, the model does an okay job. However, the model is doing a very bad job for low strength values and for high strength values. We wish that these points would like be on the diagonal, right? So we have this, the tails are not being well predicted by our model. We want it to be like this, that would have been a better model. But it is what it is. All right, and this again on the testing set. This plot here is on the testing set. All right, I want to take a look at so now that we trained this model, we have an elastic net model that has coefficients for all or some of these different weather variables, depending on what hyperparameters we used and how much of a penalty we applied. So for us to see those coefficients, if you just look at the final spec object, it is just setting the model and the hyperparameters, but it has not actually fit that to the data, at least not the way that it's showing us. So we need to plug that into this fit function that we give, again, the formula we gave before, and we need to bake our weather, and now is our weather data. So, this is even a little bit more interesting to think about. So now I want to apply this fit to the whole weather data, because I want to see what would be the parameters when you include all 688 observations. But then, of course, I have to bake it with our recipe that has been prepared. Man, all these words kind of sound weird, but but if you run this, it basically runs that model for you with your with all the weather variables that remain in this model and their coefficients. So now, if you connect this to a function called tidy, which comes from, I guess, the yardstick package. I thought was from the broom package, but if you give that on tidy, you just get that output on a more, tabular format. So that tidy just makes this output that before was like what it was not really a data frame, just puts that into a data frame. And then I just want to arrange the estimate column from the highest to lowest, so we can see which variables in our data set had the largest coefficient associated with them, meaning that they had the largest impact on fiber strength. So if I come here, we can just do an arrange, and I want a descending order. So we use the desk function for that, and we call that on the estimate function. So, well, I guess a couple of things to note before we talk about the estimates. So one of them is that we only have 37 model terms, at least on my side, when I use I think my penalty was equals to 1. So on my side, I ended up with 37 rows or 37 predictor variables in my model. We started with 72, if you remember. So on my side, at least, that I used the parameters that I think was mixture 0, penalty 1, that was the best on my side. I ended up with 37 only. So we dropped a lot of the other ones. And then the coefficient of each one of these are in descending order. So in my case, mean day length in August was the most important, followed by mean day length in October, May, and June. Then we have the intercept, and then we have some other variables here. The last thing that we're going to do here is just to do a similar thing of what we did here, but then make a plot. I want to tell you the following thing. We're going to be using a function here that comes from the VIP package that stands for variable importance. In our case, in the case of a elastic net model, variable importance is calculated just this would be variable importance for an elastic net model. It's just the size of the coefficient from each one of those variables. So in our case, we did not need to use the VI function from the VAP package to do this. We already have that data. The reason I'm showing you how to use the VI function from the VAP package to get variable importance is because we're going to use that on random forest as well. And in random forest, we're not going to get coefficients like this. We will need to use the VI function. So just to show you how you would use a similar approach regardless of the algorithm, I want to show you the next step here, which is using the VAP package. So we're also starting, so the beginning here is the same. So final spec, fit, and tidy. Or I guess we're not tidying here, but final spec, fit, and then the function that we're missing here on those 3 dots is a function called VI that comes from the VIP package. If you don't connect yet with the below code, you just stop here and you run it. This is what it's going to give you. It's going to give the variable name, the importance, and the sign. So whether that coefficient was positive or negatively associated with strength. The remaining of the code here is just doing some wrangling to make the plot nicer. So if I add a pipe, I'm just getting the absolute importance. So here, I guess the coefficient, if we have variables that are negatively correlated, the coefficient could be negative. So we're getting the absolute value of that, and then reordering the variable by sequence of importance, which makes a difference when we plot in ggplot. And you're going to see that in a second here. I have this lice head equals to 10. We can just comment that off for now. And then I'm just bringing in ggplot where I have the importance on the x-axis, the variable on the y-axis, and whether the sign was positive or negative, and then just doing a geom call as well. So if we run all this, this is what you should see. So, this is actually interesting because I don't think this is the same. So here is saying that the largest importance is coming from mean solar radiation in September. But I don't think that was the highest estimate here. So maybe, yeah. So maybe they're not the same. I guess I just learned something. But when I ran this the first time, they were matching, or maybe I was confused. Anyways, if we look at the variable importance here, is really giving us that how important of a given variable is for the prediction or for how the model performs. So we're seeing solar radiation and mean solar radiation and minimum temperature in September being 2 of the most important variables in this model. A very similar output is what you would get from random forest, other models as well. So that's again why I'm showing you how to do this with this code. All right, and of course, if this is your paper, you do want to try to interpret these, right? So why is solar radiation in September driving cotton fiber quality? Or in this case, cotton fiber strength specifically, right? So there are explanations for this that we can further explore, but these are the most important variables in weather variables explaining cotton fiber quality, in this case, strength. All right, so a quick summary here. we cover a lot today. What I would recommend you to do is, we had a lot of concepts that we applied. It is confusing. I expect for you to be confused. What I would propose is that you come, if you really want to understand what's going on, come back to this code, rerun again, maybe try with different data, right? You're gonna have, my goal is for you to learn and implement this to your own situation. You have this scaffolding of what should be done. Now you can come here, bring different data, different recipe steps, different grid types. You know, I mean, there's a lot of things you can change here, but this is the scaffolding that you can use. And I would propose that at least you come back and rerun this on your own, trying to understand what each step is doing, how each step is connected to the next, because this is a workflow that everything connects. So, quick summary, we talked about penalized linear regression, so ridge, lasso, and elastic net, and the different types of penalties. We set up our machine learning workflow to train an elastic net model, where we use the recipes package to process data, the R samples package to split the data. We created a fixed grid to search the best values for mixture and penalty. We use a 5-fold cross-validation as a resampling method. We utilize both R-square and our MSE as the metrics to both assess the best model or to select the best model. So that was a question I think Pramod had the last time, is when do we use these metrics? I hope in this exercise you were able to see that we're using the metrics both on the resampling side to select the best hyperparameter values, and also in the end, when you're assessing the predictive ability of that model, right? And then once the final model was determined, we use it to predict the test set, which had not been seen by the training step at any point, and then evaluated that with predicted by observed, R-square, RMSE metrics, and variable importance. So again, if this is your first time running machine learning model, congratulations, you just did it. So any questions?
Our research is up for 1 year or 2 year with the data.
Okay.
So for each plot, we have the same with the data. On that scenario, is it possible to do predict yield on different rate of our treatment?
Using weather? Yeah, so no. Because if you're measuring weather at the site level, right, then it means you have one value for each weather variable for all plots. So we're not gonna really be able to say, well, you know, when I applied X rate of nitrogen and I had rainfall of X amount in June, I had highest yield. I mean, you can say that, you know, if you have multiple years, then you bring the weather variability from year to year. But if you have just one, or even, I mean, in machine learning, if you have less than 100 years or side years, it's really difficult for you to really, because imagine, for example, when doing your faults. So first off, you have let's say you have 100 side years, which I know you don't, and most of us don't. But if you have 100 side years, which is a lot, you split 70 on the training, 30 on the test. So 30, you just don't look from the beginning. And then 70 data points, you're gonna use to then do a five-fold cross-validation. So you split that 70 into 5, right? So it's really limiting how much you can really learn from the data if you don't have enough data points. What you could do on your side is, for example, if you collect, and I know you're gonna have this, you're gonna have hyperspectral data from a trial. So gonna have your treatments, your plots, right? So treatments and reps, and you're gonna have all these columns of different wavelengths. You know, depending on how many treatments you have, how many plots you have, how many sites you're bringing into this, you could make the case that you have a okay size to try some of these algorithms. Still, we're probably not gonna have more than 1,000, I don't think, which I guess is that boundary of kind of between 500 and 1,000 is where, you know, you would get the most benefit. But yeah. But maybe if you think of variables that you're measuring at the plot level rather than at the site level, like weather. Any other questions? All right, so let me get your attendance. Make sure you save, you stage, commit and push. Want to get your attendance. And I do want to tell you all one thing before you leave. So I was under the impression that we could have classes past the last day of classes, the official last day of classes, and I learned we cannot. So what that means is our schedule got shortened by a couple of meeting times compared to what I originally thought we would have. I updated the schedule, so you can check that. So our last class is gonna be on April 25th. Because if not, the next date, I think, is May 1st, if I'm not getting wrong. And the last official day of class is April 29th.
Can bring the class up to April 29th.
Up until April 29th? Yeah, but I think that the next one is past that.
But people often do change the class time to. It is up to April 29th if they need to. If need to.
Oh, okay. So you're saying like,
So you can see
Yeah.
that Friday to 26, April 26.
do you really want to learn more? Yeah. Yeah, that could be challenging from my side, though. I mean, I really, I thought that we could go all the way to May 7th, but that's what I had originally. So with the way that it is now, we only have 2 more meeting times that I want to introduce you to 2 more algorithms. One's going to be conditional inference tree and then random forest. If we had more time, I would wanted to expose you to boosting algorithms like XGBoost, which is one of the most important ones. But I think before we get there, we have to do some groundwork before getting there. So I don't want to skip ahead. And then my goal, maybe for next year when I teach this again, is to show you all how to develop Shiny apps and have interactive dashboards with the result of training your data and creating models in a way that you can deploy what you learned to someone that doesn't know how to code. Again, this year, I don't think we're going to be able to. If you're interested in those, I can always, share some resources. You can explore on your own and learn on your own. I can always serve as a resource as well. If you run into issues. But really, my goal here, which I think is what we're going to accomplish, is once you understand the workflow of machine learning models, which we just did today, it's not that much complicated to just adapt to different models, right? So going through this workflow today, and when we go through the other 2 algorithms, you're going to see that most of the steps are going to be very similar. We're just changing a few things here and there. So the workflow, at least, you will have learned. And then, it's going to be easier for you to learn on your own if you have to. All right, I think that's it for today. Thanks, everyone.
Hey, Dr. Bastos,
Yes,
can I shoot you a Zoom link and could we troubleshoot the error I was having?
yes, let's do that. When I get
Thank
to
you so
that,
much.
I'll join that.
Yes, sir. Thank you.
Thanks. Bye.